Hello, geometry. This is 2.1, conditional statements. We're going to do some stuff in class with these explorations. This chapter 2 is a completely new realm, new area, new discussion. You're going to be like, well, how does this fit into geometry? And it's not necessarily a whole lot of shapes, but part of geometry is learning how to deal with logic. So it's actually a lesson on logic and arguments and making good arguments that defend what you want to do. So what we have with 2.1 are called conditional statements. So statements that have to meet certain conditions for things to be true. So a conditional statement can be either true or false. So it can either be a yes or a no. So these symbols right here, P implies Q. P implies Q. Conditional statement, P with the arrow pointing to Q. It can be written as an if-then statement. So if this, then that. So an if-then statement might be, if I can run 100 meters in 9 seconds flat, then I will go win the Olympics. So an if something, then something else. The P is called the hypothesis, and the Q is the conclusion. So we have hypothesis and conclusion. We're now in English class. So an example would be if a polygon is a triangle. So there's the hypothesis. Whatever follows the if is the hypothesis. Then the sum of its angle measures is 180. That would be the conclusion. So that makes a conditional statement if, then. So I'm going to skip over this exploration, and I'm going to jump past the vocabulary. That should be filled out after Chapter 1 test. And we're going to get right into some of this information here. So I've written down some more examples. Okay. So here's the conditional statement term again, definition. When it's written in if-then form, the if part contains the hypothesis, and the then part contains the conclusion. Okay, so this is read P implies Q. If P, then Q. So the instructions may be write this as an if-then statement. So write as an if-then statement. And sometimes you'll need to change some words around or even add words. So the statement might be, all birds have feathers. So as I think about this, all birds, so if I'm a bird, then I have feathers. That's your statement that we just said. So I'm not going to say, though, if I'm a bird, because I'm not going to be a bird. I'm going to say if an animal is a bird, then it will have feathers. Okay, that could be an if-then statement. All birds have feathers. If an animal is a bird, then it will have feathers. You are in Kansas if you are in Gossel. Notice the if right there. This is the start of the hypothesis. So this is your hypothesis. This will be our conclusion, Q. Just like here, the animal is a bird, that's hypothesis. Conclusion is it will have feathers. So to write this as an if-then statement, we're just going to switch it around. If you are in Gossel, then you are in Kansas. We have put it into if-then form. If, then. Negation. The negation of a statement is the opposite. So it's kind of like just putting the negative sign in front of a number. To write the negation of a statement P, you write the symbol for negation. So this right here, this is a squiggle mark. That is a symbol for a negation. Also refers to as similar to in other times, but right now it's negation. And it's read not P. So not P. So the words are not P, the symbol is the squiggle mark P. So if they say write the negation of the statement, the ball is red. Write the negation. So if this is P, the ball is red, the negation, not P, would be the ball is not red. That is it. We just put the word not in there. If the statement is the cat is not white, if this is P, then the negation, not P, would be the not of a not. That's a double not. We would say the cat is white. It's the opposite of what you have. So we have a conditional statement. P implies Q. We have the negation of a statement, not P, or not Q, or either one. The following three things are going to be all related, using with P's and Q's. And we'll have to know them. We have the conditional. So this is just our standard conditional. P implies Q. So this could be if I jump, then I fall. Okay, I don't know, made it up. If I jump, then I fall. So this makes P the if I jump part, the I jump part. That makes Q the I fall. So this is a hypothesis, I jump. The conclusion is I fall. The next term is referred to as the converse of a conditional statement, and that switches the Q and the P. So exchange the hypothesis and the conclusion. If Q, then P. So this was if P, then Q. If Q, then P. So this would be if I fall, then I jump. That's the converse. So we have conditional, if P, then Q. Converse, if Q, then P. The inverse is if not P, then not Q. So you negate both the hypothesis and the conclusion in that order. If not P, then not Q. So if I don't jump, if P is I jump, then I don't fall. Okay? If I don't jump, then I don't fall. If not P, then not Q. So conditional, if P, then Q. Converse, if Q, then P. Inverse, if not P, then not Q. And the final one is on the next page. It's called the contrapositive. Okay? The contrapositive of a conditional statement. First, write the converse, then negate both the hypothesis and conclusion. So if not Q, then not P. Okay? So not Q implies not P. So if I don't fall, then I don't jump. Or didn't jump. If I didn't fall, then I didn't jump. Okay? So we can put a kind of past tense there when we get to the contrapositive. If I don't fall, then I don't jump. If I didn't fall, then I didn't jump. So a conditional statement, this is important here, a conditional statement and its contrapositive are either both true or both false. Okay? So conditional and contrapositive are going to be linked together. Similarly, the converse and inverse of conditional statement are both true or both false. So converse and inverse are linked together. So a conditional and its contrapositive, and converse and an inverse when we're talking about how things are true and false. So in general, when two statements are both true and both false, they are called equivalent statements. When two statements are both true and both false. So we have the statement, all numbers are awesome. Yes, we know that. We know that to be true, right? So our conditional, if P, then Q. How can I write this as an if-then statement? So all numbers are awesome. So let's say if I have a number, then it is awesome. Okay? That agrees with the statement. All numbers are awesome. If I have a number, then it is awesome. So this first part here, if I have a number, that's my P. This part right here, that's going to be my Q. Then it is awesome. Converse, flip it around. If what I have is awesome, then it is a number. So you notice even when I flipped it around, I had to change a few words to make it make sense, make it sound okay. So if what I have is awesome, then it is a number. Okay? Is that saying the exact same thing as a conditional? Conditional starts with a number and says, this number is awesome. But the converse says, I have something awesome. It must be a number. it is not saying the same thing. So these two statements are not not logically equivalent. Okay, they're not equivalent statements because I could have something else that's awesome. I could have a Michael Jordan rookie card or LeBron James. Okay, I could have the coolest cat in the state. Okay, that would be something that would be awesome. Okay, I could have the most awesome math teacher of all and the one who cares about me the most. Okay, but I guess I could be a number there. Okay, so inverse, not P. Let's keep going here. Not P implies not Q. So here, if I don't have a number, then I don't have something awesome. Again, converse and inverse. Those are always both true and both false. So we already said this one could be false, should be false. Because we have other things that are awesome besides numbers. This says if I don't have a number, then I don't have something awesome. Well, you can still have something awesome even though it's not a number. Our statement just said all numbers are awesome. It didn't say numbers were the only thing that is awesome. Okay, so this one's going to be false as well. We'll call that first one true. The conditional and the contrapositive should always be both true or both false. So let's write the contrapositive, which is the negation of the converse. So if I don't have anything awesome, then I don't have a number. Okay, that would be true. If I don't have anything awesome, I know that I don't have a number. Okay, because if I had a number, I'd have something that's awesome. So conditional, converse, inverse, and contrapositive. Moving on to what they call biconditional statements. Conditional statements that go two ways. They have a word if and only if. So biconditional statement that contains the phrase if and only if. And it's when all four statements are the same. So conditional, converse, inverse, and contrapositive. If they're all true, you can write a biconditional statement. So this can be used when all four statements are true. So when it works both ways. Conditional is true, converse is true, inverse is true, and contrapositive true. So any definition can be written as a biconditional. So let's rewrite this as a biconditional. If an angle is a right angle, then its measure is 90 degrees. Okay, make sure you're not just watching me. If you're stopping, writing down the example. Let's write it as a biconditional. Usually the if and the then are going to go away. So I drop the if and the then, and I'm just going to say an angle is a right angle if and only if, oops, no apostrophe on that its measure is 90 degrees. So an angle is a right angle if and only if its measure is 90 degrees. We don't have to write it the other way. Okay, this is a statement that the conditional, converse, inverse, and contrapositive would all be true or false. Second example, if two line segments are the same length, then they are congruent segments. So here's your if, there's your then. Let's kind of take those out, and we'll say two line segments are the same length if and only if they are congruent segments. If and only if they are congruent segments. Okay, we've seen some of these examples already. I'm not going to spend a whole lot of time. Let me get one thing over here. Going over these examples because I've tied some into the definitions there. No, maybe not. Maybe we should. Okay. So number one, rewrite the conditional in if-then form. 13x minus 5 equals negative 18 because x equals negative 1. What is your hypothesis? What is your conclusion? Well, this is happening because of this, so this seems to happen first. So I'm going to say if x equals negative 1, then 13x minus 5 equals negative 18. I'm going to write it like that. The sum of the measures of an interior angles of a triangle is 180 degrees. This one can kind of be confusing. You have to think of an if-then statement. So what's my hypothesis? What's my conclusion? The conclusion is talking about something being 180 degrees. That is the sum of the measures of the interior angles. So if you have a triangle, so if I have a triangle, then the sum of the measures of the interior angles is 180 degrees. Okay, and here's just practice with the conditional statement, converse, inverse, and contrapositive. Decide whether each statement is true or false. Keep in mind the conditional and the contrapositive, they're linked together. So they should either both be true or both be false. Same with the converse and the inverse. Okay, so we can go over that in class if we need to. I'm going to look real quick what they call truth tables. This is something that's not in the notes. I'm going to give you a paper copy of this so you can kind of follow along. You should have that. Get that out now. Truth table, these are used to determine conditions under which a conditional statement is true. This is important here. A statement is only false when a true hypothesis results in a false conclusion. Okay? When you're dealing with logic, when you're dealing with some of these examples here, a statement is only false when you have something that didn't happen when you were expecting it to happen. Okay? So an example might be, if you study, then you'll pass. Okay? If you study, then you'll pass. So, does that mean you'll pass if you don't study? No. Okay, remember the converse and inverse are not logically equivalent. It does mean if you didn't pass, I know you didn't study. The negation of the conclusion means the negation of the hypothesis. But if I study, then you'll pass. So the only way you can prove this statement false is to study and not pass. So if a true statement results in a false conclusion, then you have a false statement. Now, if you did not study and you still passed, I can't make a conclusion. I'm going to call that true. Okay? So if the hypothesis doesn't happen, we can't make any conclusion about this whole thing, and we call it a true statement. Okay? That's kind of one of the weird things here is if the hypothesis is false, the whole thing is going to be considered true because this did not happen. Okay? If I ask you, example earlier we talked about is if you buy a dog, then I'll buy food. Okay? If you don't buy the dog, I'm not obligated to buy the food. So that statement is null and void. We're okay. It's going to be called a true statement. So these are going to be set up for you like this. We have a conditional, P and Q. Hypothesis can be true, true, or false, false. The conclusion can be true, false, true, false. So this is how we always set it up. And these are the four combinations that we have between P and Q. True, 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 false. I can have a true hypothesis, true conclusion, true hypothesis, false conclusion, false hypothesis, true conclusion, false hypothesis, false conclusion. So P and Q will always be set up this way. So P implies Q. The only way to get a false statement is to have a true hypothesis and a false conclusion. So a true hypothesis, a false conclusion, that results in a false statement. True, true is true. False, true is true. False, false is true. If the hypothesis is false, it's going to be true here. Okay, and that's the first part here. Don't always think about the hypothesis, but you have to think about what's coming first. For the converse, we're going to go true, true, false, false, true, false, true, false. It always starts off like that. Now the way we're going here, we're going to start with Q. Q implies P. So Q is the first one we look at. So anything that has a true first part and a false second part. So true first part, false second part is going to be false. The rest are going to be true in this case. Okay, because we're starting with this. The conclusion has become the hypothesis. Whatever is written first is the hypothesis. The P and the Q are now just representing values, numbers. Okay, so this goes true, true, that's true. False, true is true. True, false is false. False, false is true. Contrapositive. So P, true, true, false, false. Q, true, false, true, false. Not P. The negation of P would be false, false, true, true. Negation of Q is false, true, false, true. So contrapositive, we want not Q as the hypothesis, so this is coming first. False implies not P. So false, false is true. True, false is false. False, true is true. True, true is true. Isn't that exciting? Lots of trues and false. I want you to notice this true, false, true, true is the same that you get for the conditional. True, false, true, true. That means these two are logically equivalent. Inverse. Set it up. True, true, false, false. True, false, true, false. Not P. False, false, true, true. Not Q. True, oops, sorry. False, true, false, true. So not P implies not Q. So false, false, I'm going to start with the not P column. False, false is true. False, true is true. True, false is false. True, true is true. So we've shown converse and inverse. This is how we show that statements are equivalent. The converse and inverse have the same resulting pattern. True, true, false, true. Conditional and contrapositive have the same resulting pattern. True, false, true, true. So if they say create a truth table and they want P implies not Q, this final column over here is what we're going for. So we're going to say P and Q. So true, true, false, false. True, false, true, false. Okay, we need a not Q. Not Q. Negation of Q would be false, true, false, true. So here we go. P implies not Q. I'm going to put my answers right here. So I'm starting with P, and then I'm looking at not Q. So that's true, false. That is a false statement then. True, false is a false. That's the only way to get false. True, true is true. False, false is true. False, true is true. That's what you're going for. That's your answer right there. Okay? The negation of P implies Q. What I would do in this case is we already know this. So we already know P implies Q from up here is true, false, true, true. So the negation of P implies Q would be false, true, false, false. You fill in like that. Okay, thank you for your patience. I know this is a lot. We still have even more to cover in class, but hopefully you go back and this gives you a basic understanding of what we're doing with this. This is, again, logic. It is a part of geometry. We're going to use it in our proofs and our theorems and postulates that are coming up, and we'll keep plugging away with this. So let me know what questions you have the next time we see each other, and good job hanging in here till the end.